Welcome to this sequence of videos on the Hausdorff distance. There will be two parts. This is part one. And as before, we start from the real space with the Euclidean distance, or the Euclidean norm or Euclidean distance. And we are now interested in measuring the distance between two sets, let's call them A and B, which are in subsets of Rd. Okay, and I'm not specifying now if they are closed subsets or convex subsets and so on, subsets of Rd. So let's make a first attempt to measure the distance between them. And this is called the directional Hausdorff distance, and we will define this distance, h, from A to B, okay, to be the supremum over all possible points in A. Okay, there will be vectors in Rd. Infimum over all small b in B. Okay, and now when we have small a and small b, we take the distance between them, which I will write like a minus b, the difference in Rd, and the Euclidean norm. Okay, that's the distance between 2 points. Okay, so this is going from A to B. Let's make a little picture here that will demonstrate. Suppose the set A is this circle, this is A, and B is this ovalic shape. Touch it, don't touch it, doesn't matter. Okay, so if we look at this definition, we find the point in A which is the farthest from B, but take the closest point in B to A. So let's say those will be this point small a, and this will be this point in B. And this distance measures what is the longest distance for me to start from the set A until I first step in set B or arrive to set B. Okay? Now, as you can imagine, if I flip the order here and write delta h b comma a, I will have a different distance measure. The closest point, okay, this is A prime here on A, and this is B prime, okay, in B. That's the supremum. Now I'm taking over points in B. That will be a much longer distance to start from the worst place in B and to reach the first time at a set A. So in terms of properties for this distance, we see that there might be a problem here. But first of all, we can say that the distance between A and B is indeed non-negative. That's fine. Okay. We can also say that if the distance is happen to be 0, we'll see in a minute some examples, it means that, okay, A should be in the closure of B. Okay, is a subset of B closure, and if B is a closed set, then it's a subset of B. Okay, so let's see a picture here that will tell us how this can be. Okay, here is a circle which we'll call the set B, and set A is somewhere inside B. Okay. I can take the farthest point in A in B, but always, since B includes A, the infimum is whatever A I choose in A, I can choose the same number, the same vector in B, and get to a distance equal to 0, and that's where A is in B. If I was looking at the other direction, I'm flipping the A and B here, okay, in this distance. Yes, I can get away from A to this point, let's say in B, and even if I find the closest point in A to that point, I still have a distance. Okay, so the other way around, it's not true that B is included in A. Of course, we can see that in the picture. Okay, so because of that, one thing that is violated here that we already saw in this example is not necessarily, okay, equal to BA. Okay. However, if we think about the triangle inequality, this is satisfied. Okay, so dA going from A to C is going to be less than if you have to go through B first. Okay, so you go from A to B, and then from B to C. Okay, that triangle inequality is working. It's just the symmetry that is violated. So this is not a full metric on the set of subsets. Okay, on the collection of subsets. This is a semi or semi-metric. Okay, how can we remedy this issue? Okay, and this brings us to the definition of the Hausdorff distance. So the Hausdorff distance, which I will use the letter D sub h, between A and B, distance between two sets in RD, A and B, is going to be equal to the maximum of two numbers. One is the directional distance going from A to B, and the other one is the directional distance going from B to A. Okay, those are two numbers as defined here. Which one is bigger? That's my Hausdorff distance. Okay, so now what, of course, will happen is that it's positive or non-negative. It is, okay, so dh, let's write it down. dh of AB is always non-negative because both of them are non-negative. It also is true that dh of AB equal to 0. If it is equal exactly to 0, then the closure A is equal to the closure B. And if they are both closed sets and they are equal to each other, symmetry, by definition, is going to work here. Okay, and this is true now. Okay, so this symmetry works, and the triangle inequality is working as well. So going from A to C is less or equal than the distance from A going to B first, and then dh going from B to C. Okay, so that's correct. There is an alternative definition for the distance. Okay, dh of AB, the Hausdorff distance between A and B, can also be written as the supremum over all the directions in the unit sphere, the dimensional unit sphere, of the absolute value of the difference between the support function evaluated at u here minus the support function of B also evaluated at u. Okay, if I look at the supremum of all directions of the absolute value of this difference, it is equal to the Hausdorff distance. This is a very useful result. Similarly, we can also define the Hausdorff norm. So if we look at a certain set A, its norm, the Hausdorff norm of that set, is going to be defined to be the Hausdorff distance between the set A and a set that includes just the origin. Okay, so that's the Hausdorff norm. So, and it's also, we can write it equivalently to be equal to the supremum used in the unit sphere, d minus 1, and now only d, or the, sorry, h of a like that. So, okay, like that. Because the support function of the 0 is 0 all the time, so it's the same definition, or the same result. Okay, let's see some pictures just to see the triangle inequality, that it's working in our distance. Okay, so if this is the set A, let's say this is the set B. Okay, and this is the set C. Okay, don't have to be the same shape. Going from, let's talk first about the this distance, the delta. Okay, if going from A to B, okay, in this case will be standing the farthest from B and getting to the closest point in B, which will be here. And then going from B to C will be, again, starting from the farthest point in B from relative to C and getting to the closest point in C, which will be here. And going from A to C directly will be the same because they are aligned. So this is not a demonstration why the triangle inequality doesn't work. It's line. So we need to have some kind of a triangle construction here. So let's look at this example where this is A, this is B, and this is C. Okay, this now looks more like a triangle of circles. Of course, going from A to B will involve this point and this point. Going from B to C will involve this point. So both distances are double the radius or the diameter. But going from A to C is just the diameter once. Okay, so it's 2r. Basically, what's written here is like 2r less than 2r plus 2r, which is obvious. Okay, so this is the triangle inequality, which works for the directional distance, but also, and of course, also for the regular Hausdorff distance. Okay, so this is the definition of the distance, the Hausdorff distance, and more properties and more results on the Hausdorff distance in the next part of this sequence on the Hausdorff distance. Thank you for watching.